the work we've been doing for a few years on trying to move the molecular simulation fields towards a more machine learning kind of approach, and maybe telling you what's in for you, no? So what type of tools and models and data we've built that you can use. So the idea is that you can, if you want to simulate these objects, there are several ways to doing it. This would be, you could say, okay, I forget about the electronic structure and I can of course grain that into the average forces, and I get a level of representation of my molecule, which is just with the nuclei. And this is kind of the approach that you have in molecular mechanics. You could also keep the degrees of freedom of electronic structure, but you can also kind of decide, okay, I don't want the hydrogens. They are actually in molecular mechanics just point charge carriers. They almost don't interact in terms of energons. That's the only purpose they have. And you could have more and more cross-graining things. And one cool thing of doing this approach using kind of a potential, which is machine learning, is that while before these things were all different stuff, there was a group doing cross-graining with their own codes and stuff, another group in doing mechanics, another group doing DFT and so on. Now you can treat all of these things with similar data and with similar tools. And this is what kind of the underlying structure that we've been using. And we've been working on trying to push this approach forwards. Annie started with a transferable model, machine learning models for, transferable, I think it's probably Annie. Bella Parinero did it before, with just small molecules. Then we've been working in having transferable models for cross-graining system. First, just carbon alpha system, and then mostly recently with kind of no hydrogen system, as you saw before. Then there's how to go from here to system where you represent the molecule, where you simulate the system in terms of complexes or ternary complexes and so on. Now you add the solvents, so there is work to do here. We've been working on this too. We have something internally on this. And but I'm gonna only present what is relevant for the conference here, which is the drug discovery bit, which is mainly on the small molecule. And so we call this force field AceFF. What is it? So the idea, as I said, is that you want to interpolate the energy function, and instead of having a fixed functional form like you have in Amber or Charm, you get it through an interpolator. Sorry, this F is not force, it's function. And it depends on coordinates, some parameters, atom elements, and charges. So if you add spin, you have the entire quantum state. So you can say, with given this information, I should be able to compute an energy surface over that or interpolate it over that. And if this function here is differentiable, then you can compute forces. There are certain things that you need to guarantee, some physical constraints, so you want some symmetries. There are different methods that you can use to do these interpolations. And but essentially, this is what you're doing. So we're just interpolating with some physical constraints. So we've been working on building up the tooling and the architecture for this. So initially we built a neural network architecture, which was, so all this neural network stuff started mainly through materials, because they really don't have anything else to use apart from BFT. And but they don't kind of mind how slow is their machine learning architecture, because the alternative is DFT. But for that discovery, the alternative is molecular mechanics. So we have a totally different kind of scenario here. So we're trying to use, so they usually use spherical harmonics and a lot of complicated, numerically complicated things to run. we're trying always to be have a level of accuracy which is okay, so comparable to but be faster than what materials folks were doing. And at the moment we're using this model. I'm not saying it's the last model, but it's a reasonable model, and we have a tool which is both of these are available in GitHub, and which have tool set for an ecosystem for integrating all of these things. Then we build a data set. We built several, but I'm gonna speak all about this one, which is the one we use for creating the SSF models. We took PubChem and we kind of clean it of a lot of things. It gets to around 1 million molecules, and we took all the elements that we kind of care of. We took the level of theory, QM level of theory, the highest we could afford, and we started building, and we included charged molecules, and we started building this data set. First, the version 1 with 10 million configuration with of only 20 atoms. Then we have another set which is also complete now with another. We added another million with some sort of active learning to decide which configuration we need to pick. And now we have the last one where we really focused on charges and we build multiple models. So how do we assess the models? So one quick way is to look at the Cellar torsion scans. So these are the public data sets, nothing to do with us. We just take it, and we have 3 models at this point. We have the one that is trained on, actually we have more models. One that is trained on the 1.0 means it's trained on the 1.0 data set. 1.1 is trained on the 1.1 data set. TensorNet is a graph network, and you can have certain level of message passing. The more message passing layer you have, the more many body terms you have, but it's more expensive. So you want the least the least layers, but you want the more layer you put, the better is accuracy, and the larger is the receptive field of this thing. So we test 2 models, the 1L and the 2L, and this is just for reference on this torsion scan how it goes with XTB. MACE is widely recognized as one of the most accurate model in materials. There is the large model and the small model. AIMNet is also a new model. ANI is a model which was a kind of start all of this. Then we have our 1.0, 1.1. At this point, when we are down here, we don't necessarily optimize for this benchmark. So you see, from 1.1 to 1.0 from 1.0 to 1.1, we actually went a little bit higher. But even already 1.1 is at the level of MACE large. Same level of the best machine learning model. We 1.2 beta L. 1.2 beta is because we only have 50% of the data set, so we will retrain it once we are 100%. It's kind of a checkpoint of that. Yeah, we are practically like MACE. Another data set that you can compare on is this Wiggle, which is 150 highly strained conformations. And we compare against multiple models here. And again, we are mainly interested in faster models. We'll see later why. And yeah, so we are kind of half of the error of ANI and a bit less than AIMNet in this case. AIMNet would be a kind of a more accurate version. So it's a totally different architecture, but kind of serve the same thing. This is another test that we use a lot because we care about doing RBFE with these things. So we just took all the Schrödinger molecules and the Schrödinger molecules in the Schrödinger data set for the public binding free energy benchmark. We compute the FT forces, and then we kind of produce this plot where in one axis you have the energy and in the other one you have the force. And you see that at the beginning we had really good performance in electron volts, divided by angstrom. We have really good performance on neutron molecules, but not so much on charged molecules. This is called by charge. 1.1, we get even better performance on the neutral molecule, which is what we tried to do, but still kind of the same slightly better, but not much better. So here, compared to here, we added more charge molecule. 1.2, as I said, we focused on charges, so we just added a lot of more charge molecule, and we get a lot less error on the charge molecule. And you can see that it's not so much of a difference if you use the better model or the not as accurate model, faster. It all depends on data, essentially. Data has driven these things more than the model itself. Speed for us is important. So the AceFF 1.1 with the one layer is actually kind of the similar speed compared to ANI, and almost 10 times faster than MACE. So what's in for you? So all these models are available, and we plan to make a 3-month release. So every 3 months, we make a release. The more feedback we get, what this doesn't work, the more we can put the DFT data in, and the more, and in 3 months later, you have a model. For instance, now we add in DNA data, because there was somebody that is doing RBFE on DNAs. And so how do you get it? You just go to Hugging Face. You can use it. The license is, you can use it, test it, experiments with it. If you do a commercial use, then you should talk to us. But for anything else, doing papers, doing comparison, do whatever you want. Then you can download it from here. So if you go in this collection, you will have all the things. There are collabs notebooks to use it. Also the ATM code that we use, taken from Emilio and rewritten a little bit, is also publicly available. And so you could also do RBFEs. We might have a collab at some point on this as well. And so if you go to here, in the README, there is all the documentation, comparison, and so on that you can use. Okay, so what's in for what happened when you use this stuff for RBFE? So we've done already something like this in 2020 last year, using Gianni. So this, and we show that if we take GAF2 and we treat in a kind of an QM-MM kind of approach, where the small molecule is treated as an NNP, so it's treated with a force field, and the rest of the system is still treated as MM. We get already an improvement in correlation. Essentially, the only thing we're doing is improving the ligand strain. So now the force field of the ligand is totally, so the ligand's interactions with itself are all given by the neural network potential, but the intermolecular forces with water and with the protein are still given by GAF2. So we're just changing this thing. We were in fact expecting much, but actually the improvement is quite significant already. And this was with ANI. So ANI is pretty good. It gets to FEP, I think this is OPLS3 kind of level, more or less. GAF is pretty decent too. So we couldn't get, like, in the previous paper, we compare with OpenFF and so on, we couldn't get it to be better. We haven't tried the latest one. But anyway, so FEP was better or slightly the same level, but there is an improvement, consistent improvement every time you go from GAF to ANI2X. The problem with ANI2X, it just only works for is trained for non-charged system. There's and also it's a limited element set. So we down with this latest paper, we just use, well, it's called AceFF now because there's a trademark for AceForce. We tested on these for against OPLS4 now, and you can see that again it's better than GAF. It's OPLS4 is better in RMC consistently. in terms of a candle, there's not much of a difference. Sometimes AceFF is better, sometimes OP-less is better. It's more a balanced outcome. But let's see in 3 months. This is still 1-0. We also want to compare with ANI on the subset of system that we can run ANI, so on the neutral one. And okay, AceFF is significantly better in any dimension. So we're not losing anything by using these things. It's better on all the subsets. In terms of identifying the best compounds, again, this is more like in line with the candle thing, and we get very good performance of the AceFF benchmark. That's, I think, the overall kind of general rule with 1-0. Then we haven't had the time to run 1-1 and 1-2. We probably will not run 1-1 because we think it's just marginal. We want to run 1-2 because it's very expensive to run on all the subsets. So we're actually running now the 1-2 and see how it goes in terms of performance, and then we'll release 1-2 in 3 months probably time. In terms of so this is what's was interesting for us to see also was the charge transformation. So what happened when you change charges? And again, so if you have a transformation that changed charges, and again, you have FEP OP-less4 is better, marginally better. And in candle, as before, is comparable, 0.6, 0.5, 0.5. Okay, so what do we do with this, with all this? So we build this machinery, which is called quantum bind, and then we have this force field GAF, or we have AceFF. So we have a long-term collaboration with Biogen. They had a problem, which was a lack of correlation between a computational model and their experiments. They could not kind of recapitulate the SAR. And the way we tackled that was to kind of run what we call silicon conformational assay. So we just ran MD with adaptive sampling and Markov-Stein model to kind of reconstruct entirely the process and the process of binding. And we then can figure out what's the real conformation, what's the non-real conformation. And then we applied our model, and we got a lot of we got a much better correlation. And also we could kind of see what are we had actually 8 out of 10 of the most active compounds would have been identified with this pose, and we could see the critical substitution and what were the problems where that didn't happen. We also have we just started a collaboration with Cybant, with Woody, Anna, and Rafa. And it just started, so we don't have much here, but the idea is the same. No? So how do we integrate what they have with what we have, and how do we help them to get things together? At the moment, we just could kind of verify what was the right conformation, again, by proving that we had a model that correlates with experiments in a case of binding. We also use it internally, and that's actually the way we developed it mainly. So we are making an extremely low number of molecules to test. So 40, 83, 19, and so on. This is the kind of it-to-lead performance that we get by running a lot of these things computationally. So we try to be as optimal, as computational as possible in this sense, and just get the other ones. And okay, so as a conclusion, we have there is this family of all-atom force field. Please use it. Get it there, give us feedback, and you'll get a better one every 3 months. It can be used for dynamics, minimization, but we don't know. Just we tested a little amount of things that we can test. You probably know much more than us or where you want to apply it and how to use it. And okay, we have this quantum bind framework it's compatible with TorchMDNet and GAF, and at the moment we see that just even if we just handle the ligand with NNP, we can significantly improve performance compared to just GAF2. And we are now seeing, okay, how do we go further from there? And thank you so much, everybody, and to the folks in particular here on the Lex that did most of this work. Thank you so much.
Perfect. We have time for some questions.
No, that's what I meant before. No, we tested a very narrow area. Water is not even in the data set. So just to, it's, I think we put it in, we plan to put it next, to put also amino acids are not in the data set. So DNA was not in the data set. So there is a lot to build, but it's fast. So we can generate 1 million data points per month or less, and then every few months train and release. But we need to know what's working, what's not working, but no, we haven't tried. But it should be able, especially for water, you probably want a lot of correlation, a lot of the many body correlation, because you need to coordinate all those atoms. But yeah. When we did what? When we did that? No, torsional scans are so good that this, I mean, they are way below 1 kilocalorie per error. So we didn't, it was never a problem for us here. So we didn't dig too much into the, I don't know if that's what you asked. No, we just take the molecules, and I think we compute the deltas between the minimum and the other conformations, and we compute the average. Where are you? So we had to increase from 20 to 30 to get better results. I think in the SPICE paper, I think we did a comparison with model size, and it wasn't dramatic. That I don't know.
Okay, perfect. Let's thank again Gianni.